Okay, so today so first of all, my name's Keith. I'm here to talk to you today about using graph theory to build a recommendation engine in Node.js. So a little bit about me just to start. Like Zara mentioned, I'm Canadian. I have no traditional CS background. I actually went to school for biochemistry. The approach I like to take to solving problems is a very systems-oriented, exploratory approach. I like really understanding how systems work, how things work from the nitty-gritty. And kind of building from there, so understanding first principles and building out as opposed to just picking a tool that I know does the job. I'd prefer to solve it myself. I'm currently the engineering technical lead at Storefront Inc. So I am Canadian, but like was mentioned, I'm currently in San Francisco. Linked to my GitHub here, I have tons of open source work that I'm always, tons of projects that I'm always working on that I'm always pushing things out to. So I want to first cover the goals of this talk. So the goals of this talk are kind of first, this systems level approach. First we want to understand why we're going to build a recommendation engine, and then we'll tackle the how, and the how is like the nitty gritty, actually getting into writing code. So for the why, we're really going to look at resource management. So working at a small startup like Storefront in San Francisco, we don't have a whole lot of engineers, we don't have a whole lot of time, we got to iterate quickly, move fast and break things, right? So how do we manage those resources? How can we get features out in a really short amount of time, have them production ready, and sort of how do we tackle problems with that in mind? And then the second aspect is the how, and that's more of the individual contribution, individual contributor, implementation details. So let's look at the problem space here. So like I said, we had a small engineering team. When this recommendation engine was implemented, it was a total team size of 4, me included. So to give context to the company, Storefront is a marketplace for short-term retail rentals. We've been called the Airbnb of pop-up shops. So it gives you a little bit of idea. We have listings, we have users that want to book and request those listings. So the goal for this engine is really we want to increase user engagement and get more requests. I mean, we're running a small company, we're trying to make money, we're trying to get users to really interact with our site and stay on it and not really get bored and make sure they find the listing that they're looking for. So here's our solution and kind of the requirements for the implementation of this solution. So like I mentioned, this talk's obviously about generating a recommendation engine. So this recommendation engine should ideally work given a specific listing or a user. So what I mean by that is you should be able to give a listing ID to this recommendation engine and get a bunch of related or similar listings. You should also be able to give a user ID and say based on this user ID, and here's a basic idea of the listings that I think this user might be interested in. So we want to have many recommendations available. We don't want to keep repeating the same recommendations over and over. So for example, if a user refreshes a listing page, we want to be able to pick from a wide variety of listings that might be related. And this is also to really, so we have to actually put the user into context, different users. So are people with spaces, they're using Storefront to really advertise their space, right? So we want to make sure that a lot of visits go to, a lot of spaces get a lot of views and requests. So we also want this clickbait mentality. We need to keep our users entertained or really just within our system and using it as much as possible. We want to deliver this project quickly. So we have a 1 to 2 week time frame. And talking about resources, this is 1 to 2 developer weeks. So 4 developers working for 2 weeks is actually 8 weeks worth of resources. We don't want to spend that much time on a project like this. Move fast, break things. We got to get it out as quickly as possible. And we want to minimize the technical debt and the technical footprint of the project. We want to make sure it does, we want to minimize the amount of maintenance that has to be done in the future. And we want to make sure really, if possible, developers never really have to touch this again. That's obviously never the case, but we want to try and aim for that. Okay, so what existing solution did we have? So when I got to Storefront back last June, there was actually kind of this recommendation engine that already existed. It was this huge SQL query. It took 300 plus milliseconds to execute per user. It was super, super complex, a bunch of joins, nested subqueries, and really for the entire user base, it took, at the time for the user base size, it took half an hour to an hour. Ultimately, as the user base grew, it took hours to generate recommendations. So we kind of just stopped using it because it was way too unwieldy. And so that was the solution we had, and it wasn't really tenable. So the problems with that solution, like I mentioned, it was slow. 300 milliseconds for a query is ridiculous. Now, there are indexing issues there and optimizations we can do there. But there's also extreme complexity just in writing these queries, right? And it's dependent on our current database schema. So if we want to change listings, how that schema is set up, we want to change amenities that they have or really have the database is set up, we have to rewrite our recommendation engine every time we do that. That's a lot of technical debt, so it's not really something we want to deal with. There's lots of knobs and levers. And what I mean by that is in terms of product decision, what drives a recommendation? Is it space size? Is it space type, or is it amenities, whatever? You're leaving those decisions up to the developer, which is one, they should probably be up to like a product manager, and two, it's just a lot of things to think about, a lot of intellectual overhead. So that really covers the technical debt aspect. So how are we gonna solve this? Let's take the Mark Watney approach, and let's try and science the shit out of this. Okay, so introducing the graph. Now, you guys should all be, everyone here should be somewhat familiar with graphs. If you're not, I wasn't familiar a few years ago. Like I mentioned, I have a biochemistry background. I've been coding since I was about 10, but everything I know is kind of like self-taught, and I've had to approach it. So graphs a few years ago were kind of new to me. So what is a graph? Very simply, they're used to model complex relationships between many objects with nodes or vertices and edges connecting those nodes. Okay, so what is the graph-based solution to this problem? I got asked this last night. Okay, so you have this recommendation engine. How does this graph-based solution work? Our nodes are going to be our users and our listings, and our edges on the graph are going to be ways that users have interacted with listings. So it's going to be requests, favorites, and views. We've been tracking requests, favorites, and views forever since the launch of Storefront. So we have all that data in a relational database, and it really tells us how users have been interacting with the website. Now, request is obviously a little bit more important than a favorite because it shows that the user actually has, like, not only has intent, but has actually tried to actually request and book a space before. A favorite shows that, yeah, there's high intent, but maybe they haven't actually sent a request yet. And finally, a view, kind of like just looking over the listings, maybe not super high intent, but we could probably get them to convert if we keep kind of showing that to them. Okay, so what are the graph-based solution benefits? So one, it's a node. I guess we're talking about Node.js, so I'm also talking about graph nodes here. I don't want this to get too confusing. But it's essentially like node type agnostic. And what that means is we can start doing graph traversals given any type of node, and it works the exact same way. So instead of having to generate like a separate, like our old legacy system, generating a separate SQL query, for both listings and users. We can have like one solution and you just plug in, you say, okay, use this user node or use this listing node, and then do a traversal outwards. Another benefit to a graph-based solution is our users are actually going to generate our recommendations for us. So we eliminate a whole lot of complexity in terms of actually trying to decide like what makes one listing related to another listing. Another benefit is that graph traversals are super fast, especially if we're essentially just doing a breadth first search outwards, like wicked fast. So that's awesome compared to our 300 millisecond not optimized query. That was just a nightmare. Okay, so what technologies are really available to do this? Obviously, this is a Node.js conference. We're going to tackle this in Node. But how can we really set up our graph? Well, we could use Neo4j, which is the leading graph database software, and there's other software out there. The pros are it's well supported, it's well documented. The cons, are there any cons? I mean, well, anytime you bring a new tool on, your entire team has to get up to speed with how to use that tool, read the documentation, make sure they're super familiar with it. We have a team size of 4 engineers. Our problem space isn't super large. We just need to generate these recommendations. So let's go like insanity wolf on this. Let's kind of fall into the, maybe it's a little bit of not invented here syndrome, but let's just build a graph ourselves. So I proposed this to people, and the very first reaction from some developers is like, why would you do that? That seems silly. But if you actually think about the problem that we have here, it's actually fairly simple. Graphs involve very simple data structures. It's just referential data structures between nodes and edges. We have the benefit in Node.js that when you're running a Node server, because of asynchronous non-blocking I/O, Node has shared memory and shared RAM between every HTTP request that comes in. You can have essentially a shared state. So we can keep a graph alive in RAM without having to offload to a different service. Another benefit at Storefront is we're already running multiple Node.js backends anyway. We have a custom API server and framework that I kind of built off-site and co-opted to be used for a lot of Storefront services. I might get into a little bit about that later, but it's called Nodal. It's awesome. I love using it. We're running at least 4 services on it, I believe. So now let's get into these nitty-gritty technical details. How are we going to build a graph in JavaScript? Well, let's start off with something basic, just so conceptually we can see that we can actually set this up really easily. So we have this concept of, let's just set up a really simple relationship and say this dude Joe, he really likes to play Minecraft. So we have 2 nodes, we have Joe, we got a game, we got Minecraft, and we have this edge connecting the 2. So we have some very simple, all of this is going to be in ES6. we have some very simple JavaScript here, just creating these objects as object literals. So our nodes obviously require an input array because a node could be connected to multiple edges, an output array, and that's for directional graphs, directed graphs. We give it some properties like name Joe. Our edge is a little bit different than our node in that input and output should just be an object or a null reference if an edge kind of just doesn't lead to anywhere. So we create our objects and then we kind of link them together. Our edge is kind of the glue that holds the structure of the graph together, and just very simply without any high-level manipulation or whatever, we have a basic graph structure already. So really, what do our nodes and edges need? Well, there's some shared properties between nodes and edges. So we have like entity types that would belong to both nodes and edges, just for really quick and easy identification of like node types or edge types. So an entity type might be, in the previous example, we had person like Joe, and we had game like Minecraft. So in the context of storefront, what we're going to be using it for, our entity types are users and listings. Then we also have attributes and property lists just for actually querying and traversing the graph. We're going to want to be able to set different properties on nodes. Say if you're looking for people of a certain age, you might have age as a property, et cetera. So what are the different as we, what are the non-shared properties between nodes and edges? Well, for nodes, you need input edges, which should only accept an edge data type. That should be an array. Output edge is the same thing. Whereas an edge only takes one input node. It can only connect one node to another node. So it doesn't need arrays there and should only accept a node data type. So this is a good case for inheritance. You can use composition here as well, but we're just going to go with one of the tools we have in our tool belt, which is ES6 classes. I'll get to that in a second. So we know that nodes and edges have some things in common, but they don't have everything in common. So the things that they have in common we'll put in a base class, which we'll call a unit here, and everything that's separate functionality for the node and the edge will really create their own classes that extend from this base unit class. So let's use that handy ES6 class syntax. So keep in mind here, there's like a little bit of like a holy war, I guess, going on about using ES6 classes. A lot of functional programmers really don't like the paradigm or the design pattern of trying to force classes into JavaScript. It's a tool, it's useful, it's easy to reason about, and it's easy for newbie developers coming in from other languages, which is really important on a development team, especially a small engineering team that you're trying to grow out and scale really quickly. So keep in mind that classes are just syntactic sugar over prototypes. If you don't understand the basics of prototypal inheritance and the difference between like really what class is doing, I recommend you read up on that, but that's not, it's kind of out of scope of this chat. So let's look at this base unit class first. So here's an excerpt of our unit class. We have a constructor which takes entity and properties, some type coercion there, a little janky, but load up the properties as well. Make sure our unit also includes methods to actually modify the properties object. So set, unset, get, has. We're going to create our node class and extend it from unit. So our node class is actually really simple because the majority of our graph constructor of actually assembling our graph is going to be associated with the edge, because the edges are kind of the glue that holds the graph together. So we just set our data structures that we need. So we have an input edges array, output edges array, and we have this unlink that's going to reference this edges unlink that we haven't quite tackled yet. So our edge is a little bit more complicated because it's going to need a lot of functionality as an object that really glues our entire graph together. So our edge is going to need some sort of link methods to link two nodes together. It's going to need some sort of distance. So for a weighted graph, you need to be able to represent distances between nodes in different ways. The edge needs to have some sort of indication on whether it's a duplex connection or not, so whether or not it's bidirectional. So on a directed graph, it might only go in one direction, but an edge can actually go both directions as well. And then we also need this unlink method that we referred to that is really going to handle the cleanup from removing all the references in the arrays on the node and on the edge itself. Okay, so that's just a basic overview of our, here we have a basic overview of our edge class. There's a lot more code associated with, well, not a whole ton, but a significant amount more code associated with these other methods. So now let's re-implement our basic graph. Instead of using object literals like we were using before, just using these new objects we've created. So now we have this syntax that this interface that is pretty easy to reason about, kind of really hard to mess up. It's just simple for a developer to look at and kind of understand what's going on. Instantiate new nodes, set some properties on them, we create a new edge, and then finally, like I said, the edges are the glue that holds the graph together. So we're going to use that edge and then link Joe to Minecraft. So the order of arguments that you put in the link determines the direction of the edge, unless the edge is duplex or bidirectional, in which case it doesn't really matter. Okay, so let's add a little bit more complexity to our graph. So we have this like linear relationship of like Joe liking Minecraft. So now we have this concept of Notch, who's the creator of Minecraft, and let's add him onto the graph. So we're just extending this graph linearly right now, but as you can see with just 2 lines, we can really easily create a new node and create a new edge and just kind of start extending our graph. Now we still have a linear graph, so what does a larger graph look like? Well, here, still going with the theme of Minecraft, we have Mojang, the company that invented Minecraft, created it. We have Microsoft, which acquired Mojang. And we have Jennifer, who also happens to really like Minecraft as well. So she recently purchased it. And then Minecraft just prints money for Microsoft at this point. So we'll add another edge for that as well. Very simple, straightforward syntax. And we'll kind of look at the result of our graph here, this awesome ASCII version. I'm terrible at Photoshop, so I just use ASCII art instead. Okay, so we see here we kind of have this like cyclic structure. So this is more complex. It's not just a linear graph. So we can see how this, these simple base classes can really be used to create this like larger, more complex graph structure from basic first principles. Okay, so what is our actual implementation and our setup? Like I talked about earlier, we have our nodes. So now back in terms of the recommendation engine and the graph we're going to be generating for that. We have our nodes, which is our users and our listings. We have our edges, like I said, requests, favorites, and views. And how are we actually going to set this graph up? So we're going to basically break this down into 3 steps. One is we're going to query our relational database where we already have all this information. We already have all of our users stored. We already have all of our listings stored. We already have all of our requests, favorites, views, etc. So we want to query that relational database and store everything in arrays in memory. Cool. We don't have like an absolutely ginormous user base. We'll get to like edge cases and complexities with larger code bases in a second. But we'll query our relational database, get all this information into arrays. We're good. From all that information, from those arrays, we then want to essentially map them to create node objects and edge objects associated with each of these types. And then finally, our 3rd step is kind of linking all of our nodes together. So going over all of the edges, linking all of our nodes, and actually creating our graph structure. Okay, so what does this look like? There's a whole lot of code here. We have the first part of this code sample is just kind of like, it's almost like pseudocode. It's just showing that this user's listing, views, favorites, and requests, they're all just going to be, here they're represented as like synchronous function calls, but you can populate these asynchronously. As long as whenever you get into this method of setting up your graph, all the data that you need from your relational database is available. That's the most important part. We have this getNodeById method that's really going to go through all of our nodes and just return the appropriate node given an ID. It's a really dirty, quick ON, time complexity N function to just grab the nodes. We actually use something we end up creating this larger graph class that takes care of this all for us, but this is just a hacky way to just start implementing this. We're going to map over our users array. So users is an array type. We're going to map over it, change our users instead of just being this database relational DB data. We're going to turn them into actual node objects. We're going to do the same with all of our edges. So there's a lot more code here. We're going to map over our views and then link the appropriate nodes with those edges as we map over them. So this is really creating this more complex graph structure. Okay, so things to keep in mind as we're creating this graph structure. So this is entirely in RAM. Everything here is in a single thread being processed in Node.js. So it's probably not the best solution for gigantic data sets. If you're working at a company and you guys have tens of millions of users, hundreds of millions of users, probably not the best approach. Storefront isn't quite there yet. In those sorts of scenarios, you'd want to actually step out of Node and probably start using something like Neo4j. But the benefit of working at a smaller startup where we're just trying to get right off the ground is we can actually store all this data in RAM. It's not a huge chunk of data. There are many potential optimizations you can do here as well. So like island nodes, and what I mean by that, nodes that aren't connected to any other nodes, you can just kind of eliminate them from the graph. You obviously don't need to add them to the graph. So even in our, when we query our relational database and start setting up our nodes, we can just ignore something. entirely if it's not connected to anything else. Also edges, we don't want to add the same edges repeatedly, so a user might have multiple views on a listing, for example. We don't need to add an edge for every single view that a user has on the listing. One edge will suffice. So we can, in our query to our relational database, we can just do a group by and group by like the user ID and listing ID and just get one result. We only need one edge per interaction. Okay, so finally, we want to make sure our edges are weighted. Like I've reiterated a number of times here, requests are more important than favorites, which are more important than views. So we don't want our edges to be weighted equally. And it's important to note that distance on a graph is actually inversely related to the weight. So if you want something to have a really high weight on your graph, you want it to have a really short distance. So if you think about a graph traversal outwards, if something's closer, so it has a shorter distance, if two nodes are related by a short distance, it's going to be traversed first, so it's going to have a higher weight. So it's just something to keep in mind. So we'll use this edge set distance method to make sure that once we've created our graph, we just kind of want to adjust all of our distance parameters. Views are not as important as favorites or requests, so they're going to have a distance of 4. Takes longer they're further out to traverse. Favorites, distance of 2, and requests a distance of 1. And so finally, let's put it all together. We just have a code excerpt of, it's actually a much longer method than this, and there's stuff that's unexplained there. But essentially, we're going to traverse outwards from our node, whether we start with a user node or a listing node. And we're going to use a modified version of Dijkstra's algorithm. Dijkstra's algorithm is a pathfinding algorithm that deals with weighted graphs that allows you to find guaranteed find the shortest distance between shortest distance path between two nodes. So we're going to start using Dijkstra's algorithm to do breadth first traversal outwards, and then we're just going to stop when we've accumulated essentially 100 nodes that we've traversed, for example, if we want to generate 100 recommendations. So the final implementation, like I mentioned, we have this graph object that kind of combines some of these like higher level methods, like actually the traversal itself. It's an instance of your graph class. So the final API interface kind of looks like just graph.closest for a closest query. You give it a target node, which could be a user or a listing. You give it a comparison function. To say, oh, I'm looking for nodes that have the entity type listing. Give it a minimum depth of 3. The reason we do that is because if you're finding something closest nodes to a user, we don't actually want to give them recommendations for spaces they've already requested or favorited. So remember, those are at distances of 1 and 2 in the traversal away from the user. So we want to ignore those entirely. It's okay for us to recommend a space to a user that they've already viewed if they haven't transacted or like actually sent a request on it yet, because we want to encourage them. They're obviously at least somewhat interested. So we'll grab 100 different items there. So to continue with our final implementation, what we're actually going to do in production is we're going to query, do this graph traversal outwards. We're going to grab 100 different recommendations per query. So essentially, we're going to traverse outwards, grab the first 100 listings we see on this graph from a specified node, and then we're going to count those as recommendations. And from these 100, we might only want to show like 3 at a time, so we'll just pluck 3 randomly. And that's pretty easy to implement. So the final implementation continued is the graph is actually going to have its own server. Entirely, that's just going to have 2 endpoints, one for users, one for listings. We're going to regenerate the graph from our relational database once per day, ideally at midnight or like at a low traffic time, although it takes about a minute or 2 with our current loads to generate the entire graph to actually do those DB queries. We're going to cache it on disk as well. We're going to save the structure of the graph on disk. We don't repeatedly refer to it on disk, but if our server crashes, if there's a seg fault or something silly, or we're currently running on Heroku decides to shut our server down randomly, and we boot back up, we don't have to re-query our relational DB every time. We can just load it from disk, which is much, much faster. And we want to cache, we can also, an optimization we can do is we can cache recommendations for each listing, and we actually do this on our API server, not on our graph server. So we ask for 100 recommendations for a listing when a user hits that, and then we cache all of that data, because within a single day, since the graph is only generated once per day, you're only going to get the same 100 recommendations in a day. So the conclusions are, how does the new recommendation actually compare to the legacy? Well, we can now do graph traversals and actually generate these recommendations in less than 1 millisecond compared to the 300 milliseconds we had before. So we had 2 orders of magnitude increase in efficiency and speed, which is awesome. We managed to get this done in 1 week. So 1 week of engineering time is awesome, from conceptualization to actually being out in production. And we managed to eliminate the majority of technical debt that was involved in the legacy solution. So no more knobs and levers to push. Our users are generating our recommendations for us, and that's awesome. So finally, code and related projects. All of the code that you've seen here is available in a GitHub repository called Unit Graph. It's a super lightweight graph library that we just use for traversals in Node, available on my GitHub. And we also use a Node API, Node.js API server and framework that's running a lot of storefronts services that's available on my GitHub, Nodal. Cool, and so finally, acknowledgements, end of the talk. I want to give a special thanks to Jules Walter, Kelly Mothershaw, Scott Campbell, Arthur Thornton, and Trevor Stryber. These were the core people on the engineering team, including QA and product manager, that really helped me maintain my sanity when coming up with these solutions and really getting this out there and getting it out in a reasonable time. I want to give a special thanks to the Empire Node organizers for having me here. It's been a fantastic opportunity, and I want to thank you guys. This has been a lot of slides, a really heavy talk, so thanks guys for paying attention, and I really appreciate it. Finally, you can feel free to follow me on Twitter or Medium. My handle is KeithWHOR there, and this talk is actually available as an article on Medium. So if you guys want to really read more about it and see like more of the justifications and the reasoning and a little bit more of the code in depth, you can check out the Medium article or just look at the Unit Graph library. You can look at all the code. It's open source, production ready, tons of unit tests. So it's good to go. Okay, thanks everyone. Thanks for having me.
Here. Hello? Oh, okay, awesome. That was amazing. Thank you so much. So quick questions for you. Where are you spending your retirement?
Sorry?
Where are you spending your retirement?
Where am I spending my retirement?
Yeah.
Hopefully I can save enough money and buy a super cheap island like Richard Branson did.
Oh, nice.
And just hang out there. So. It's
never too early to start planning. If you were forced to play one song for the rest of your life, what would it be?
Okay, so Taylor Swift Love Story.
Oh, that's
hands down.
Perfect, perfection. All right, what was your worst subject in school?
French. As a Canadian student, we had to learn French. French was my worst subject, so.
You still don't know it?
I don't think I could say a single sentence in French, except for to maybe ask to go to the washroom. So.
Okay. Oh, okay. All right, cool. What is your most favorite thing in the world?
Honestly, writing software. I couldn't imagine doing anything else. It's what I do in my spare time. It's what I do at work. I get yelled at for it by my girlfriend, but it's something I really enjoy doing. So.
Yeah. Amazing. All right. Thank you so much, Keith.
Thanks, guys.